What I've got here today is a slightly different unboxing to what you may have seen on other videos. This is the carry case for my restored GEC Miniscope. The GEC Miniscope is a very small compact oscilloscope that was originally developed for the maintenance and repair of clandestine radios behind enemy lines. And what you're seeing in front of here is the commercial version of that was manufactured probably in the 50s. In the carry case it includes some accessories, test leads, an original cotton wound wire, but the oscilloscope itself has been fully restored. The power plug is just simply not a power plug. Depending on which way it is inserted, adjusts for the different voltage supplies. So it has a 230 volt, a 180 and 110 volt. And the war versions were able to be connected to a DC power supply, a battery power supply. On the top of the unit is this plug here where you can plug in additional units, modules. There's a CRT for a second channel. There was talk of a signal generator, which I don't believe was ever manufactured, and an IF tuning device. On the back there's these plug units here which allow you to effectively connect different signals that are going through the oscilloscope, and they're brought out. So there's the Y channel, the X channel, so you can have an XY scope. There is the sync for the time base, and also you can select whether or not the returns trace is displayed or not. And this set of pins down here is for the power connector, so depending on which way that connector is rotated determines what power supply you want to connect to. And of course there's the earthing nut down here, and the nut that's on this earthing nut is also the nut that fastens the enclosure onto the whole scope. So you take off this first nut, and then you take off the second nut, and that allows you to slide the enclosure off the scope. Underneath there are cooling openings, and this little stand here, which makes it easy to see, also provides for cooling air to get through the scope. It's got valves inside, so it does get quite warm. For such a tiny oscilloscope, it is fully featured. It has all the controls that you would have expected of a larger scope. There's obviously the brilliance there for the CRT display. There's the signal gain, X shift, Y shift. There's the sync for the time base. There's the fine control for the time base period. And there's a course control here which allows you to select 4 different time base depending on what the frequency is you're looking at. And there is a time base selector here which allows you to go effectively to XY mode or to the internal time base that is generated within the oscilloscope. The oscilloscope only has 3 tubes, and it's quite remarkable that the designers were able to get all their features that they have packed into this tiny little scope with only 3 active amplifier devices, the 3 tubes. The knobs that you see on the scope here are from World War II aircraft. They're designed to allow airmen with thick, heavy woolen gloves on to be able to control their instruments. When you compare the World War II version of the Miniscope with the more refined commercial version that I have, you can see that they share a lot of DNA. The basic controls and the features included in the World War II version are also present in the later commercialized Miniscope. My original intention was to restore the Miniscope simply by repairing whatever faults I found. But what I did find was that over half of the electrolytic capacitors had visibly failed, and the other half had either failed under test or were close to it. In addition, I found that most of the carbon compound resistors were out of spec or had failed. And the selenium diodes that were there, I wasn't sure if they were performing or not. So I ended up replacing every resistor, every capacitor, and all of the selenium diodes. The selenium diodes I replaced with a silicon diode equivalent circuit made up of silicon diodes, resistors, and Zener diodes to match the characteristics of the original selenium diodes. The design of the silicon rectifiers set the HT voltages to optimize the performance of the valves and CRT. The result is that the Miniscope probably has better than factory new performance due to the use of modern high efficiency components. The restored Miniscope uses 17 watts of power, 30% less than the specified 25 watts. The Miniscope has a measured bandwidth of about 200 kHz. By today's standards, this is entirely unremarkable, but enough for a post-war TV, radio and repairman doing house calls in the 1950s. I guess this is the part you've been waiting for. This is my old analog signal generator hooked up to the GE Miniscope, and you can see in there that there's a sine wave displayed, but also behind there is the return trace, which is not blanked out in this configuration. The Miniscope has been configured with trace blanking enabled, and so this is just to show you what that looks like. You can see a square wave here. There's very high impedance into the oscilloscope, so the spike at the beginning of the square wave is reflection back to the signal generator. With trace blanking off, the oscilloscope has no problems in displaying a square wave. If we go to a triangular wave and turn down the gain, right, the procedure here is to adjust the time base so that it's almost in place, and then increase the trigger until it locks in place. Everything, there we go. Okay, we'll try another frequency range and turn down the sync, and it doesn't have any sync and it's working perfectly. So we can increase that out. I'm just adjusting the time-based fine control. So we've got this coarse, which is the time-based coarse control, and then we've got an analog adjustment of the time base, and then the sync here, which sets the trigger level. And at the moment the sync is fully off, which is the starting position. The Miniscope manual has a very good description of why trace blanking is not normally used. I've disabled trace blanking. You can see that there's a mixture of the signal there plus the return trace on the screen as well. We've got sine wave, triangle wave, square wave. Square wave is definitely an issue with trace blanking disabled. The return trace definitely interferes with the what you see with a square wave, but then this oscilloscope was never designed to look at square waves. It was to look at periodic waves that were not square, sine waves, triangle waves. If we change the frequency, go to a different range, we change the time base, and the procedure is to get it close to sync there, and then we'll turn the sync up until it locks. Turn the gain up, so you can see there that there's both the signal and the return trace. And when you learn to recognize the return trace, it's pretty easy to actually tell it from the signal, and it's actually quite easy to ignore the return trace. So there it is, a fully restored GEC Miniscope.